For 36 hours, something rare happened, not in space, on Earth. The global system designed to monitor interstellar objects was not observing the same thing at the same time. And that detail matters more than it initially appears. When the object now designated ThreeI Atlast was first detected, it did not arrive with spectacle. There were no alarms, no urgent briefings, no emergency classifications issued in real time. Only a faint interstellar body appearing briefly in wide-field survey data before passing deeper into the inner solar system, almost unnoticed outside technical circles. Its trajectory was unmistakable, hyperbolic, too fast to be gravitationally bound to the Sun. The mathematics placed its origin beyond the solar system with little ambiguity. In that sense, ThreeI Atlast was already unusual, but not unprecedented. Astronomy has learned, in recent years, that interstellar visitors are real. They pass through silently. They do not slow down. They do not linger for explanation. They rarely explain themselves. At first, Atlas appeared to fit comfortably within that emerging category. Initial photometric measurements suggested a dark surface with extremely low reflectivity. The object absorbed far more light than it returned. Such behavior is consistent with carbon-rich material, especially bodies formed under stellar conditions unlike those of our own system. There was no immediate reason for alarm, no anomaly strong enough to challenge classification. Then observers noticed structure. As Earth crossed the orbital plane of ThreeI Atlast, imaging data began to show a faint extension projecting sunward, what appeared to be an anti-tail. In cometary science, anti-tails are familiar artifacts. They are usually optical illusions, created by perspective when the viewing geometry aligns in a very specific way. For a time, Atlas was treated exactly the same way. But the feature persisted. Across multiple observation windows, the sunward extension did not collapse as angles shifted. Its brightness profile remained coherent. Its edges did not blur into background noise. Measurements suggested a scale exceeding 400,000 kilometers, placing it beyond the distance between Earth and the Moon. Illusions collapse when geometry changes. This structure did not. And that is where the classification problem quietly began. At this point, the discussion shifted, not publicly, but technically. If the structure was physically present, then its behavior demanded explanation. A coherent anti-tail implies resistance. Resistance to solar radiation pressure. Resistance to dispersal by the solar wind. Resistance to the natural tendency of dust and gas to spread chaotically once released. Standard comet physics does offer explanations, but none that resolve all parameters at once. Unusually large dust grains could provide inertia. Electromagnetic interactions might align charged particles under specific plasma conditions. Exotic interstellar chemistry could alter surface cohesion and response. Each possibility remains grounded in known physics. Each explains part of the behavior. None fully explain the persistence. As the structure continued to be monitored, a second anomaly emerged. Motion appeared where randomness was expected. The material associated with the anti-tail did not drift outward passively under solar pressure. Frame-by-frame analysis revealed rhythmic displacement, a repeated rise and fall with measurable regularity. Not turbulence, not chaotic outgassing, not thermal noise, oscillation. In natural systems, oscillation suggests feedback, a balance between opposing forces rather than exhaustion. Gas-driven activity typically smears structure over time. Atlas preserved it. This alone did not imply anything extraordinary. Plasma systems can oscillate. Magnetized dust can respond coherently to environmental forces without any form of control. Still, the scale was unusual. During this same interval, trajectory analysis introduced another subtle deviation. ThreeI Atlast followed its expected hyperbolic path, but not perfectly. Tiny non-gravitational accelerations appeared in the data, fractions of arcseconds. Nearly invisible without long-term plotting and careful reconstruction. Individually, they were insignificant. Taken together, they formed a pattern. More notably, the timing of these trajectory adjustments aligned closely with the oscillatory behavior of the surrounding structure. Outgassing can act as a weak thruster, but such forces usually vary with rotation and surface irregularities. Atlast showed adjustments that were precise in timing and minimal in magnitude. Correction rather than drift, response rather than erosion. As Atlast moved closer to the Sun, another expectation quietly failed. Instead of brightening, the object dimmed. Photometric data indicated an albedo below 10%. Atlast absorbed light rather than scattering it. This behavior can be explained by carbon-rich compounds, which are not uncommon in interstellar material. But the dimming followed a steady curve, not bursts, not decay. Energy appeared to be redistributed rather than lost. During this phase, light curve analysis revealed periodic reductions in brightness. These dimming events repeated at regular intervals, approximately every 144 minutes. Natural comet light curves are typically noisy, driven by uneven heating, rotation, and volatile release. Atlast displayed cadence. When researchers compared the timing of these brightness modulations with the motion of the anti-tail, synchronization emerged. Two independent phenomena, one rhythm. Orientation added another layer. The extended structure associated with Atlast maintained a consistent angular offset of roughly 12 degrees from the solar wind direction. When projected outward, this alignment pointed not toward the Sun, but toward the region of the galactic center. This observation proves nothing on its own. Projection effects are powerful. Selection bias is real, but alignment combined with persistence, timing, and coherence complicates classification. As these observations accumulated, something else entered the discussion, not in data, but in time. During a critical observational window, several major Western observatories experienced overlapping maintenance downtime. The interruption lasted roughly 36 hours. In astronomy, maintenance is routine. Downtime is not suspicious by default. Yet the timing mattered. Atlast was undergoing its most rapid structural changes during this interval. When Western instruments resumed observation, the object no longer behaved exactly as it had before. Other observatories, operating outside that network, continued monitoring. Their data recorded transitions that could not be fully cross-verified. The result was not missing data, but misaligned data. This does not imply concealment. No evidence suggests intentional withholding of information. But the gap remains a structural feature of the timeline. And gaps matter. Science depends on continuity. When observation fractures, interpretation follows. By the time ThreeI Atlast moved beyond optimal range, it had accumulated a profile that resisted simple explanation. Not because it broke known laws, but because it occupied their margins too consistently. Order where randomness dominates. Timing where noise is expected. Structure where dispersion should prevail. Part 1 ends here, not with answers, but with a boundary. Because what followed next was not a single anomaly, but a convergence. And convergence is where certainty begins to thin. By the time ThreeI Atlast moved beyond its closest approach to the Sun, direct observation was already becoming more difficult. The object was receding. Signal strength declined. Resolution softened. From that moment forward, the investigation entered a different phase, one less forgiving. This is the phase where certainty erodes. Once an object leaves optimal range, no new measurements can be taken to correct earlier assumptions. No additional passes. No second chances. Only what has already been recorded remains. Inference replaces observation. Astronomers began reprocessing the data. Photometry, trajectory reconstructions, plasma interaction simulations, this time without assuming Atlas behaved like a conventional comet. Non-gravitational acceleration models were refined. Outgassing parameters were widened beyond typical bounds. Electromagnetic coupling was introduced into simulations where it had not previously been considered. The anomalies did not disappear. Instead, they aligned. One of the most consequential moments in Atlas's passage occurred as it entered the extended gravitational influence of Jupiter. For most small bodies, Jupiter is not merely a planet. It is a stress test. Its gravity disrupts fragile structures. Comets fragment. Trajectories distort. Internal weaknesses reveal themselves quickly. If Atlas were loosely bound, Jupiter should have exposed it. It did not. Trajectory data showed deflection consistent with gravitational interaction, but without the instability normally associated with structural weakness. There was no measurable fragmentation, no sudden increase in chaotic outgassing, no debris cloud trailing behind. Atlas passed through Jupiter's influence intact. This survival does not imply strength in the human sense. Natural bodies can endure extreme forces when mass distribution and internal cohesion align correctly. Still, the pattern held. Atlas resisted disruption where disruption was expected. As the object continued outward, attention returned to a question that had never fully settled: energy. Throughout its solar encounter, Atlas displayed an unusual relationship with radiation. Instead of scattering increasing amounts of light as it approached the sun, it absorbed it. Brightness decreased. Indicators of internal activity increased. This inversion remained consistent. Thermal models struggled to account for the behavior. If volatile ices were driving activity, increased sublimation should have produced greater brightness. It did not. Energy appeared to be redistributed rather than emitted. One conservative hypothesis proposed that Atlas possessed a surface or near-surface matrix capable of converting solar radiation into internal excitation without immediate release. Carbon-rich compounds, layered organics, unfamiliar interstellar materials formed under stellar conditions unlike those of our own system. Such chemistry remains speculative, but it is not impossible. Another hypothesis examined plasma dynamics. Solar radiation does not arrive alone. It carries charged particles. Magnetic fields. If Atlas possessed even a weak intrinsic magnetic structure, it could channel incoming energy along preferred paths, shaping its surrounding environment and stabilizing motion. This explanation requires no technology, only physics operating at an unfamiliar scale. Still, questions persisted. The timing of Atlas's responses remained difficult to ignore. Structural changes did not unfold gradually with distance. They appeared during specific alignments: peak solar interaction, orbital plane crossings, moments of heightened environmental stress. Atlas did not melt into randomness. It adjusted. The language here must remain precise. Adjustment does not imply intention. Reaction does not imply awareness. Nature itself is capable of regulation. Magnetospheres respond to solar storms. Plasma sheets oscillate. Rings, jets, and disks self-organize without guidance. Yet Atlas displayed these qualities repeatedly, across independent parameters. As researchers overlaid light curves, trajectory shifts, and structural motion, a more delicate question surfaced. Not about origin, but about classification. Atlas behaved neither like an inert rock nor like a volatile-dominated comet. It occupied a middle space, responsive but not active, structured but not rigid, ordered but not controlled. This ambiguity proved more unsettling than any single anomaly. During the final observation windows, brightness surged unexpectedly. Atlas intensified by orders of magnitude over a short interval, far exceeding what models predicted for an object of its estimated size. In comets, brightness surges often signal fragmentation or explosive outgassing. Atlas did neither. The structure held. Spectral data showed rapid color transitions that skipped familiar intermediate bands. The emitted or reflected light did not align cleanly with known cometary emission lines. Again, chemistry offered partial answers. Interstellar origin implies unfamiliar molecular inventories. But the coherence of the surge, its timing, duration, and aftermath suggested coupling rather than chaos. When the surge passed, Atlas returned not to disorder, but to its previous pattern: stable, dark, persistent. As the object moved farther away, resolution degraded. Details blurred. The rhythms became harder to track. Patterns dissolved into statistical uncertainty. Eventually, ThreeI Atlas slipped beyond the range where fine structure could be resolved at all. It did not announce its departure. No final transformation. No clarifying event. No definitive cast. Just distance. What remains is not a conclusion, but a record. A collection of behaviors that, taken individually, can be explained. Taken together, they resist simplification. ThreeI Atlas did not violate known physics, but it pressed consistently against the edges of what those physics comfortably describe. It revealed how dependent understanding is on continuity of observation, how fragile interpretation becomes when data is uneven, how easily expectation shapes explanation. In the end, Atlas does not stand as evidence of anything beyond nature. It stands as evidence of incompleteness, a reminder that interstellar space carries histories formed under conditions we have never experienced, that objects can behave coherently without purpose, that order does not always announce intent. As ThreeI Atlas fades back into the dark between stars, the questions it raised remain intact, not because something was hidden, but because something passed through briefly, behaved differently than expected, and left before certainty could catch up. And that silence, more than any answer, is where the unease lingers.